Thank you. Good afternoon, everyone. I'm going to present the work developed by my working group at the University of Porto. And thank you for the opportunity to be able to share it. And thank you, Alexandros, for the brief introduction. So we know that stars and planets form together from the same molecular cloud by accreting material from a surrounding disk. And because they form from the same material, the theory predicts that there should be a link between the chemical compositions of the stars and the planets. And after the correlation between the metallicity of the host stars and the frequency of giant planets was found, several studies tried to find also a link that relates the stellar composition and the properties of low mass planets. And these studies were based either on single planetary systems, on a small sample of planets, or on a statistical comparison of the overall populations. But because of these limitations, none of these works managed to find a strong correlation. If we exclude the lightest elements, when we look at the atmospheres of solar-type stars, we see that the abundance of elements reflects within a few percent the bulk composition of planets that are orbiting these stars. And meteorite measurements have shown that this is also valid for the solar system case. The theory predicts, theoretical models predict that the magnesium and silica ratios and iron over silica abundance ratios in stars and planets should remain similar during the planet formation. And once again, if you look at the solar system and we exclude the case of Mercury, because that is a particular case, we see that the abundances of these elements, so iron, magnesium, and silica, in the rocky planets of the solar system are very similar to the abundances of solar values. So this means that we can use the atmospheric abundances of these elements in solar-type stars as a proxy for the composition of the protoplanetary disk, and then relate it with the planets. So for our sample, we select planets from the exoplanet catalog that had mass and radio measurements precision above 30%, and then we constrain the sample to planets that had mass below 10 Earth masses to make sure that we are only considering low mass planets. And this left us with 32 planets that were orbiting 27 F, G, and K stars. This solid blue line for the team's people, it's the line that represents the mass radius relation for a planet that has an Earth-like composition. We see that on this distribution, above the 4 Earth masses, there is a gap between these two populations, and this gap was interpreted as a separation between the gas-rich mini-Neptunes and the rocky planets. And since we are interested in understanding how the properties of rocky planets relate with the stellar composition, we will discard these mini-Neptunes and focus only on these 22 rocky planets. So if we take these 22 rocky planets and do the same plot, so mass versus radius, we see that these planets follow more or less the line of planets with an Earth-like composition. Our sample was almost composed of planets that were orbiting stars from the thin disk, with the exception of the TOY 561b planet, that is an unusually low density super-Earth with an ultra short period that is orbiting a metal poor star from the thick disk. So for our all host stars, we collect high resolution spectra from different sources that include, but are not limited to HARPS, Espresso, Espadon, Hires, and HARPS Not. Then we go to other spectra and we correct the spectra for the radial velocities Doppler shifts. And then for each star, we combine the available spectra in one single spectrum with an increased signal to noise ratio. Then we perform a spectral analysis to determine the abundances of magnesium, silica, and iron, because these, together with carbon and oxygen, are the main rock-forming elements. Notice that TOY 561b, since it's orbiting a star from the thick disk, has a very low metallicity, but a very high content in magnesium and silica. Then we take these abundances and we apply them on a stoichiometric model by Santos et al. To estimate the iron to silicate mass fraction, because this correlates with the core size of the planet. So a higher iron to silicate mass fraction of the planet points to a planet that has a higher density, and so the planet will have a bigger core. if you look at the previous plots, we see that for a single mass, there is a dispersion of radius values around the curve for a nut-like composition. And so this dispersion could is within the scatter for the average uncertainties, but we wanted to make sure that we wanted to make sure that this doesn't have like a physical origin behind. And so we will look at the densities of these planets and compare them and see how they are affected by the composition of the protoplanetary disk. And for that, we plot the densities of the planets versus the air mass fraction of their host star. And because planets that have the same composition and different masses can still have the same density because of compression. And so to avoid those cases, we normalize all the densities of the planets to the density of a planet that has an Earth-like composition. And so we see that there is a trend between these two quantities. So this means that the final density of a planet is a function of the initial composition of the protoplanetary disk. We also see that before that, it's important to notice that the density was only calculated using observational parameters, so the mass and the radius of the planet. And the R mass fraction was calculated only looking at the stellar abundances. And so this means that if we find this relation, this is observational evidence that there is indeed a chemical link between the rocky planets and their hot stars. Now, if you look at value of the iron mass fraction of the star, there is a dispersion of densities, and this could be because of the densities, but could also have an astrophysical origin behind. And to make sure that we are not excluding any possibility, we look at the equilibrium temperature of the planets, because the flux of high energy protons that comes from the stars can influence the size of a planet, because extreme irradiation for the stars can lead to the atmospheres to evaporate of the planet, and this can have consequences and a significant impact on their bulk composition evolution. But when we look at the correlate distribution, which is the equilibrium temperature, we see that there is no correlation between the temperature, the planet density, and the air mass fraction of the star. And so, assuming that the equilibrium temperature did not change during the planet's formation and evolution, this lack of correlation tells us that the equilibrium temperature does not have a significant effect on the size of the planet. Then we go and validate our model specifically to the solar system, and we see that our predicted values for the iron silicate mass fraction of the planets agrees very well with the reference values. And it's important to notice that our model does not consider an atmospheric layer, but this in this specific case is not a constraint, because for low mass planets that have lost their hydrogen atmospheric envelope, and that are also in closing orbits, which is the case of the planets in our sample, the atmospheric buildup is very, very limited. And so even if we neglect the atmospheric layer of these planets, this does not have a significant impact in the results. And so then we plot the iron content. So this, after validating the results on a solar system case, then we applied the same, but for our sample of planets. And we plot the iron content of the rocky planets versus the iron content of the protoplanetary disk. The planetary iron content was calculated looking only at the mass and radius of the planets and using planet interior models, and we don't apply any constraints relative to the stellar composition. On the other hand, the iron content of the protoplanetary disk was calculated looking only at the stellar composition. And so we see that there is a trend between these two quantities, but it is interesting to notice that the iron content for the planets has a wider span of values when we compare to the iron content of their host stars. This is not wholly unexpected, because it has already been shown that this overall distribution of the core mass fraction of rocky planets, which relates with the air mass fraction, has a wider distribution and a wider span of values if we compare to the iron content that is predicted and directly estimated from the host star composition. There could be an explanation for this effect, and it is proposed by Agishin et al. That the iron mass fraction of a planet can increase relative to the protostellar value if the planet forms very close to the rock line. The rock line is the region where the refractory material condensates or sublimates. And if this effect is true, the trend that we found points that stars with higher iron mass fraction would have a large rockline effect. While this effect could explain some results that we found that planets with iron mass fraction are orbiting stars also with iron mass fraction, it cannot account for the case of Mercury, because in this model, the iron enrichment they predict is not enough to be able to predict the amount of value of iron amount in the case of Mercury. So in our sample, we found 5 planets that had an iron mass fraction compared to the rest of the sample. And since these planets were like more massive analogs of Mercury's, we call them super Mercury's. It's an easier way to identify them. So Mercury, during its formation, was suffered like a giant impact that stripped away part of its mantle, and this could explain the amount of iron that we see nowadays. And simulations of collision impacts predict that there should be a concentration of masses around 500 masses for these events. The problem is that these supermercuries have a wider span of masses beyond these 500 masses. And furthermore, because the collision impacts are a stochastic process, we would expect to see a continuous distribution and not this gap that we see in the distribution. So this means that collisional impact alone is not enough to explain the formation of supermercuries, and this points to the possibility of other processes occurring during the formation of these kind of planets. We recently added 6 new planets to our results, and we were happy to find that they also follow an Earth-like composition. And likewise, when we were checking the density of the planets and the iron mass fraction of their host stars, we see that the results that we found with these new data agree very well with what we have already found previously. And there was even one planet that also fell in the category of the supermercuries. And so, to take home manage to finish, the stellar abundances of iron, magnesium, and silica can be used to infer the bulk composition of rocky planets, even if they are orbiting stars that are in different populations of the Milky Way. And in this sense, the upcoming Gaia data will be crucial to provide more insights on these relations for stars specifically of the thick disk, and reinforce the results that we obtained, because in our sample, we only had 1 star of the thick disk. All the rest was of the thin disk. So this will need a bit more work. Also, the relation that we found between the planetary composition, iron mass fraction, and the stellar mass fraction is not a one-to-one relation. So this means that the slope is steeper than 1, meaning that the planetary iron mass fraction is larger than the stellar mass fraction. Finally, the superhertz and the supermercury appear to be 2 distinct populations with different compositions, and this implies that there should be differences in the way that these planets were formed. And with this, I finish. Thank you.
Oh, thank you. Thank you very much, Barbara. Perfect timing. We have one question, Luis.
Yeah. You mentioned that Mercury is anomalous in its abundance because of the impact that they had in the past. But then why do you use the Earth as a standard? Because the Earth suffered also a very big collision early in Theia when the moon was formed. So wouldn't Earth also be very anomalous? And in that regard, it seems to me strange that it lands almost on top of Venus. Venus and Earth are very similar, despite Earth having had this big collision.
Yes. So first of all, when we refer to Earth-like composition, it's important to specify that we are mainly distinguished between giant planets that are mainly gas, that have a very important gas counterpart that the rocky planets does not have. And also, the giant impact that Mercury suffered affects in a much higher scale than the impact that Earth suffered with Gaia, because even though there was that impact, we see that the composition of Earth is still very similar to the rest of the rocky planets of the solar system and compared to the solar values, while Mercury has an unusually higher quantity of iron than what would be expected if we compare to the solar values. That's why you say that Mercury is kind of an exception compared to the rest of the rocky planets of the solar system.
Okay. And congratulations, a very nice talk.
Thank you.
Yes, we agree. Is there any other question in the audience? No? Do we have any online? No? Yes. We thank again. We are our